In last class, we discussed about the different types of biasing techniques in the JFET and MOSFETs. Today, we will discuss about the small signal AC equivalent circuit for the JFET and MOSFET. It is the equivalent model of JFET and MOSFET which is used in analysis of small signal FET amplifier. We know drain to source current of JFET is controlled by the gate to source voltage. Yes, so that's why we are always making this gate to source as reverse bias. The change in the drain current due to the change in the gate to source voltage can be determined by using the transconductance parameter. We know GM, it is equals to GM equals to change in drain current to the change in gate to source voltage. So we can write from the delta ID equals to GM into delta VGS. The another important parameter of JFET is dynamic drain resistance. It is RD. It is given by RD equals to change in VDS by change in drain current ID value. When you consider the VS equals to 0, we already know it is drawn between the VDS and the ID castings, VI castings of JFET by considering the VS equals to 0. Yes. So the amplification factor mu of JFET is defined as, it is nothing but an amplification factor, voltage amplification factor, is nothing but change in output voltage to the change in input voltage. Other it is nothing but change in VDS to the change in VS value by considering the ID is constant. So from this, these three are the important parameters of JFET. The relationship between these three can be given as amplification factor mu equals to dynamic resistance RD into transconductance factor GM. Figure shows the small signal low frequency AC equivalent circuit for N channel JFET. So N channel JFET. So in this we are considering the IG equals to 0. So gate current IG is 0 because the input impedance is very high. So where it is considering it as a open circuit value. Yes, the output is represented by the RD from the drain to source. So here we can consider the equivalent circuit VGS gate to source voltage. Here it is considered as a common source. So source is in between common to both input and output. And input is gate and output is drain terminal. In this, output impedance is represented with the RD. It is from drain to source. Yes, the current passing in the drain is ID. We can write it is equals ID equals to GM into VGS value. So we are written it is equals to current symbol GM into VGS value. So whatever we applied voltage between the gate and source is VGS. Here you can observe. Next, analysis of FET amplifier. So JFET and MOSFET can be used in three configurations similar to your BJT. So in BJT we are having the emitter, base, collector. So in FET also we are having the source, drain, gate. The source, drain, gate, three are analogous to the three terminals of BJT. So whatever the source in the FET, it is analogous or similar to the emitter in the BJT. Similarly, drain terminal in the FET is similar to the collector in the BJT, and gate terminal in the FET is similar to the base terminal in the BJT. So now we can configure the FET in three ways. One is common source, that source terminal is common to the both input and output. So in this case, input node is gate and output node is drain. Second one is common drain. Here drain terminal is common to both gate and source. Gate terminal is at input node and source is at output node. And third one, common gate configuration. In this, source terminal is connected the input node and drain terminal is connected the output terminal. Yes, these are the three different configurations of FET, either it is a JFET or MOSFET, any one of that met. A common source amplifier with bypass capacitor. Yes, so here we are discussing about the common source amplifier with bypass capacitor. In this, we are using the voltage divider biasing. So in this voltage divider biasing, you can observe the circuit diagram, voltage divider biasing circuit with the bypass capacitor. Clear? The above figure shows the source amplifier with voltage divider biasing. So in this, you can observe the equivalent circuit diagram. So we know this R1 R2 resistor forms the voltage division. This voltage divider circuits, voltage divider network R1 R2 both are parallel. We know the equivalent R is equals to R1 is parallel to the R2. So it is become RG value. Yes. So in the equivalent circuit, when considering R1 R2 are parallel, it is gate side. Yes. And this RD is the drain resistance. So in this equivalent model, we already know equivalent model we are having by default VGS into GM and RD value. It is drain resistance, dynamic drain resistance. And here we are having the capital RD. So this RD is acts as a load. So here we are connecting the drain to source. Drain to source, and here RC is not affected because we are having the parallel capacitor. Here all the capacitors, that C1, C2 and CS, all the capacitors are short circuited. Yes, so all the capacitors short circuited. So due to this CS capacitor short circuited, this RS will not affect, so RS is 0, and this DC biasing VDD is also short circuited. Yes, so from that we draw the equivalent circuit model of this common source amplifier with voltage divisor and bypass capacitor. Yes, in low frequency model all the capacitors are short circuited and DC supply also short circuited. We need to calculate the input impedance, output impedance and voltage gain. So input impedance is calculated by observing from the input side. So in this input side we are having only, we can observe only RG value. RG is nothing but parallel to parallel resistors of R1 and R2. ZI input impedance equals to ZI equals to RG, so it is nothing but R1 parallel to the R2 value. Output impedance is calculated by replacing the VI is short circuited. That means VI equals to 0. So then when VI equals to 0, therefore gate is short circuited to the source. VS equals to 0. Hence we can write GM into VS equals to 0. Why? Because VS equals 0, we can write GM into VS, product term becomes 0. Then output impedance, now looking from the RD resistor, then we are having the Z0 equals to small rd into capital RD. Small rd into capital RD. These two are parallel to each other. Yes, if dynamic resistance RD is more greater than the capital RD, then what we can write? Z0 is almost equals to the capital RD value. Yes. Next, voltage gain. This voltage gain is always defined as output voltage to the input voltage. So we can write output voltage is nothing but VDS and input voltage is nothing but VGS. So V naught by VI equals to VDS by VGS. We already know output voltage, we can write it is equals to, in the circuit diagram, minus gm vgs into parallel resistance of output impedance. It's nothing but parallel resistance of small rd and capital RD. It's nothing but output impedance. So output voltage can be written as current passing through the output impedance. Here output impedance equals to small r is parallel to the capital RD, and current passing through the resistor equals to minus gm into vgs. From that we can write AV equals to voltage gain equals to V naught by Vi equals to minus gm into RD is parallel to the capital RD. Again, when dynamic resistance, when dynamic drain resistance is greater than the capital RD value, then we can write AV equals to minus gm into capital RD value. Yes, here negative value or negative sign indicates the phase shift between the output voltage and input voltage. So either it is a common source amplifier or in common emitter amplifier, this amplifier will provide the 180 degree phase shift from the output to the input. Yes. So this negative sign indicates the 180 degree phase shift between the output voltage and input voltage. That's about the common drain amplifier here. So in this common drain amplifier is shown in the figure. In common drain amplifier circuit, input is applied between the gate and source. So common drain amplifier is nothing but common collector amplifier. It is also nothing but common emitter amplifier in BJT. Here it is called emitter follower amplifier in the BJT. Here source follower amplifier. Yes, common collector amplifier is similar to the common drain amplifier in the FET. Common source amplifier is also called as emitter follower amplifier because we are taking the output across the emitter by considering the common terminal as emitter. Yes, here we are saying it is a common drain, but we are keeping the common terminal as source, but we are taking the output across source terminal, so it is called source follower or common drain amplifier. So in this we are applying the input between the gate and source, and output is taken between source and drain. Output is taken between source and drain. So here again DC power supply is short circuited in the equivalent model. Drain is grounded. Yes, thus common between thus drain is common between the input and output. You can write here. You can observe in the equivalent model, simplified equivalent model. So in this RG resistance is connected between the gate and drain or source. Why? Because this is connected to the grounded, and current passing here it equals to Gm into Vgs, and dynamic drain resistance is Rd, and here it is Rs is the source resistance. Output is taken between the source and drain. Yes, this is the equivalent model of common drain amplifier. Clear? And next, here we need to calculate the input impedance. Input impedance is nothing but by looking from the input side. So again, it's nothing but when I am looking from the input side, it is almost equals to the Rg value, gate resistance. So input impedance equals to Rg value, and similar to the output impedance, to calculate the output impedance, we already know replace the Vi with short circuited. Yes, so Vi value must be short circuited. So we are short circuiting the input value Vgs. Therefore, gate terminal is grounded. Therefore, gate terminal is grounded. By applying the KCL at node A, you can observe in the figure. By applying the KCL at node A, then it is equals to entering current I0 equals I0 and Gm Vgs. I0 plus Gm plus I0 plus Gm into Vgs. These two are the entering current. It is equals to leaving currents that are IRD plus IRS. So from that what we can write V0 equals to minus VGS. In the figure we can write V0 equals to minus VGS, and I0 equals to V0 by RD plus V0 by RS plus GM into V0. By taking the common as V0, we can write 1 by RD plus 1 by RS plus GM. So we know output impedance equals to V naught by I naught. So Z naught equals to V naught by I naught. It is equals to 1 by RD plus 1 by RS plus GM. So we can write it is equals to 1 by 1 plus 1 by 1 by RD plus 1 by RS plus 1 by 1 GM. So in this equation we can observe these three resistors RD, RS and 1 by GM. These three resistors are parallel to the each other. So this equation represents the parallel combination of the three resistors. So from that we can write Z naught equals to RD is parallel to the RS is parallel to the 1 by GM value. Yes, if drain dynamic resistance is greater than the RS value, then we can write equivalent value is RS. So we can write Z naught equals to RS is parallel to the 1 by GM value. So voltage gain we already know AV equals to V naught by VI. So V naught equals to we already know ID into RD is parallel to the RS value, and ID equals to GM into VGS value. So we can write V naught equals to, just we need to replace the ID value in the above equation V naught, then we can write V naught equals to GM into VGS. RD is parallel to the RS value. By applying the KVL value, we can write VI equals to VGS plus V naught. VI equals to VGS plus V naught is replaced with GM into VGS. RD is parallel to the RS. So now we can write AV equals V naught by VI equals to GM into VGS into parallel resistance of RD and RS by VGS plus GM into VGS. RD is parallel to the RS. So by simplifying here, we can write GM is parallel to the GM into RD parallel to the RS value by 1 plus GM into RD parallel to the RS value. If RD value is more greater than the RS value, then we can write equivalent resistance equals to RS. Then we can write AV equals to GM into RS by 1 plus GM into RS. If GM into RS value is greater than 1, then we can write AV equals to voltage gain. This voltage gain in the common drain is always less than or equals to 1. Yes. So in common source also voltage gain is always less than or equals to 1. In common drain also voltage gain is always less than or equals to 1. Maximum voltage gain can provide in common drain is unity. In common collector is also unity. Yes. So common collector and common drain are both are looking similar. These two are analogous to each other. Yes.